All right, so related to implicit differentiation, where we multiply by the change in x and we multiply by the change in y, what we're going to do is start applying that stuff and use related rates. So in this case, instead of when we take the derivative of x, we write a dx, which is the change in x, we're going to write a dx dt, which is how x is changing as time progresses. If we take the derivative of y, we're not just going to put dy, we're going to put dy dt, which is the derivative of y as t is changing, or how is y changing as t is changing. So this one, I think I'm just going to do one video because it's pretty short and straightforward. So for number 1, what we have on your homework is going to be y equals the square root of x, which I can rewrite as x to the 1/2. And what I will do is just take the derivative of both sides. It's the same process as what we've been doing. The derivative of y is 1 dy dt, and then the derivative of x to the 1/2 is 1/2 x to the negative 1/2 dx dt. And in the notes, we have given that x is 16 and dx dt is 8. And we have that on the second part, x is 36 and dy dt is going to be 6. So I have one variable here, one variable here, and one variable here. And so I'm going to end up solving for the missing variable. So I'm going to rewrite this one. I've got a dy dt equals a 1 over 2 square root of x times dx dt. So on the first part, now I can solve for, actually pause that for 1 second because I'm going to go back and erase. If I were to divide both sides by dx dt, which means it disappears here and picks up here, what do you do when you have a fraction divided by a fraction? You end up with dy dt times dt dx. And then your dt's reduce because that's how time is changing. And since it's in the same context, the time is going to change at the same rate, which leaves you with dy dx, which is implicit differentiation. So we're just kind of sort of adding a new layer to this whole thing and saying, well, time can progress as well. So it's essentially the same thing as what we were doing with implicit. We're just introducing the concept of time as well. So on the first one, if I'm given that x is 16 and dx dt is 8, that means I know this variable, and that means I know this variable, which means I can find how y is changing with respect to time. So it gives me a 1 over 2. The square root of 16 is 4. And then dx dt is 8. So I end up with 1/8 times 8 is going to be 1. So what that means is, as x is changing at 8 units per whatever our time is, so let's just say 8 centimeters per second, then your y is changing, or your vertical is changing at 1 unit per second, or 1 centimeter per second, whatever our distance is being measured as and whatever our time increment is. So you're just kind of sort of breaking down slope into 2 different formats. So if dx is changing, or if x is changing at a rate of 8, then that means at that point, y is changing at a rate of 1. So your slope would actually be 1/8. So anyway, that's what that means. So the second part is going to be this, and I'm just going to go back to my original equation. I have dy dt this time. So that gives me a 6 equals a 1 over a 2. Root 36 is 6. And I am looking for dx dt. So remember, that's one number. It could be a fraction. It could maybe not be a fraction. But to get that by itself, I'm going to multiply both sides by 12. Because this ends up being 6 equals 1/12 times dx dt, which is going to give me a 72 is dx dt. So your horizontal movement is 72 units per increment of time, where your vertical change is going to be 6 units per increment of time. So now we have, you can do number 2 because it's a circle. You can do number 3 because we did it in class. All right, so let's do number 4. We have the radius of a circle is increasing at a rate of 3 centimeters per minute. So the radius is increasing at a rate of 3 centimeters per minute. Find the rate of change of the area. So I'm trying to find how area is changing, which means I'm trying to find dA dt. So the first thing I notice is it's talking about area of a circle, and I know that the area of a circle is pi r squared. I've got 2 variables. Remember that pi is a number. If I take the derivative of both sides, I end up with dA dt is going to be 2 pi times r to the first, and then you have dr dt. So my question is, how is the area changing? So I'm looking for dA dt at the moment that the radius is 37. Well, we're also told that the radius is increasing at 3 centimeters per minute. So dr dt is 3. So this is 3. This is still a 2 and a pi and a 37. So 6 times 37 is going to be, good heavens, I don't know. 6 times 37 is going to be 37, and 6 is a 42, and a 180 is 2. Here we go. 222. So dA dt is 222 pi. So your area is changing at that rate, as long as your radius is changing at a constant rate. So now we can do another one. A spherical balloon. So we're talking about a balloon that's a perfect sphere, which is a 3-dimensional figure. It is inflated with gas at a rate of 600 cubic centimeters per minute. So first of all, I need to know what this affects. Well, if I inflate something with gas and it's 3-dimensional, that's going to affect the volume. So the volume of a sphere is 4/3 pi r cubed. And I'm trying to find the rate of change of the radius. So as the radius is changing, what is going to happen? Which means I am looking for, how does the radius change? I am looking for dr dt. So if I take derivatives, the derivative of v is 1 dv dt. Remember, pi is a number. So I'm going to drop my 3 out front, so my 3's reduce. And I'm left with 4 pi dr dt. And then I forgot my r squared. Sorry. Drop your 3 out front. There's your pi. Drop your exponent by 1, dr dt. I am looking for dr dt, which means I still have 2 variables. I have an r and I have a dv dt. So a spherical balloon is inflated with gas at 600 cubic centimeters per minute. So this affects the volume. This tells you how the volume is changing as time progresses. So 600 is dv dt, and I got a 4 pi r squared times dr dt, and I'm trying to find out what dr dt is. So you're given 2 different options. One is going to be when the radius is 30, and one is going to be when the radius is 55. So if I just isolate dr dt, that means I'm going to divide both sides by 4 pi r squared. So I have 600 over 4 pi r squared will tell you how the radius is changing as time progresses. So shoving a 30 here, remember when you put that in your calculator, do 600 divided by 4 pi times 30 squared. Make sure your denominator is in parentheses. And then swap that out with a 55. So we have a cube. So if I'm going to work, actually you can do a cube. I will set up the surface area for you. Actually, let's just do this one. All right, so we have, I'll do this one and then we'll do a couple harder ones. So all edges of a cube are expanding at a rate of 2 centimeters per second. So I know a cube is a 3-dimensional object and all the edges measure the same. how fast is the surface area changing? So if all the edges are the same, let's just call that E. E for edge. I want to know how the surface area is changing. Well, how many surfaces are there? There's a top and a bottom and 4 sides. And since it's a cube, they're all the same. So that means the surface area is going to be E squared. Sorry. Because E times E is E squared. But how many of those do I have? I have 6 of them. So that's how I'm going to measure the surface area. And it says that the edges are expanding at a rate of 2 centimeters per second. So I was given dE dt at 2 centimeters per second. So I want to know, how is the surface area changing? So this is not S times A, this is just surface area. So the derivative of one surface area is dSA dt equals the derivative of 6e squared is 12e to the first dE dt. And this is not the E of natural logs and Euler's number. This is just E for edge. And I'm told that dE dt is 2. So I am trying to figure out how fast the surface area is changing. So I'm looking for dSA dt is 12 times my given value of 2, which is going to be 24, times whatever E is. So if each edge is 3 centimeters, then I'm going to plug that in at 24 times 3 and get a 72. So that means the surface area is changing at 72 square inches or square centimeters per second. And then if I plug in or substitute in a 15, 24 times 15 is going to be 240, and then another big number. So that, whatever that is, that's going to give you that value. So that is the easier one. So I'm going to come back with a harder one.